Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will talk about another popular probability distribution, the negative binomial. As usual, we are going to start our discussion with an example, and then we're going to try and generalize what we learned from that example. Okay, so this is an old example. We discussed this kind of a situation when we introduced the geometric probability distribution. But you'll see that there's a slight difference. Okay, so before, when we were talking about the geometric distribution, we talked about something like this, a random experiment similar to this one, but the random variable was defined differently. Okay, so let me remind you what we did. Right? What's the random experiment? And then I'm going to underline what's the difference between what we did back then with the geometric distribution and what we're going to be doing now with the negative binomial probability distribution. Okay, so it has to do with finding Pepsi drinkers. Remember? And well, these guys had historical records that suggest that Pepsi has a market share of 26%. Okay, and they want to conduct a new taste test, right? And for that they need Pepsi drinkers. So what they do is they contact, randomly selected soft drink users from that population, right, of soft drink users. They identify Pepsi drinkers. Okay, so back then, when we talked about a geometric distribution, what we wanted to know, the random variable of interest, right, let's call it X, was the number of soft drink users until we found our first Pepsi drinker. Our first. Note that in this case, instead of being interested in finding the first, meaning how many we need to contact until we find the first Pepsi drinker, we are interested in the number of soft drinker users that we need to interview until we find the fourth Pepsi drinker. Okay? And what we want, our task, is finding the probability distribution of this new random variable y. Okay? So first, let me, to save a little bit of time, let me go and find in our lecture notes the characteristics of the experiment, right? They are going to be the same as they were for a geometric probability distribution. Okay, so let me find those so we can save a little bit of time. Okay, I'm back. I found them, right? I went and checked our lecture notes corresponding to chapter 3, right? And I retrieved these characteristics again back from that example when we introduced the geometric probability distribution. So the characteristics of the experiment are the same. So we have a sequence of identical trials, and well, the point is identifying a Pepsi drinker. Each of those trials results in one of two outcomes: a success or a failure, right? A success is going to be when we identify a Pepsi drinker, and a failure otherwise. We are assuming that 26% is the probability of success, right? The probability of finding a Pepsi drinker, and that probability remains constant, right? It's the same from one trial to the next. Another important assumption: independence. Okay, so we have the same experiment, but the random variable of interest has changed. Okay, so let me remind us about new random variable, how it's defined. It's the number of trials until the fourth success occurs. Okay, so we want the probability distribution of y. Again, let me remind you, when we ask for the probability distribution of a random variable, what we want is a list of possible outcomes with the corresponding probability. Okay, that's it. So we either provide a table, which is something convenient when we have a finite number of possible outcomes and they are not too many, or we provide a formula, right? Okay, but we need those two ingredients: possible outcomes with corresponding probability. Okay, now let's think about this. Okay, what are the possible values for our variable y? If we are talking about the number of trials until our fourth success, well, we have to at least try 4 times, right? So that would be the first value of our random variable, y equals 4, right? Okay, now using the characteristics we described a minute ago about the random experiment, talking about those characteristics of our random experiment and using the labels that we presented there. So y equals 4, when the random variable y assumes the value of 4, would be equivalent to the following event: S intersection S intersection S intersection S, right? Okay, now again, going back to the description of our random experiment and assumptions, an important assumption is that of independence. So we're assuming that we have independence. So by independence, that probability, the probability of an intersection, becomes just the probability of S times probability of S times probability of S times probability of S. So what we end up with is the probability of S to the 4 power, right? We have probability of success to the 4 power. Okay, Now, well, the probability of success is 0.26. So we have 0.26 to the fourth. Okay. So that's our first probability. Let's find it. What we're going to be doing is we're going to find probability similar to this, but for 5 and 6, and then we're going to try and generalize and come up with a formula for the general case. And note that in this case the possible outcomes are the set of numbers k, let's call them, such that k is greater or equal to 4. Okay? Well, let's find the next probability. Probability that y equals 5. Okay, so if we needed 5 trials to get our fourth success, that means that something like this occurred. We had the following sequence. First a failure, and then 4 successes in a row. Okay? That's a possibility. Another one would be, well, guess what? The first one was a success, but the second one was a failure, and then after that only successes. Make sense? That's another possibility. Another possibility would be, as you can imagine, that the failure takes place here. After 2 successes, we observe a failure, and then we have another 2 successes. And the other one would be this event, that we have 3 successes, then 1 failure, and finally on the 5th trial we have our 4th success. Make sense? And that's it. Now note something really important, something that all these sequences, if you will, share. This one here, the last one, is always a success, right? And then here, you know, from trials 1 to 4, right, we could have a failure somewhere there. Okay? Now, just like before, to find these probabilities, we're going to be using the assumption of independence. Then that's going to make our lives easier. So for the first one, note something interesting. So we're going to have the probability of failure times probability of success times probability of success times probability of success times probability of success. So let me write it down like this. Probability of failure 1 minus probability of success, which is 0.26. Okay? And to be super specific, I'm going to be using the power of 1 here. And then we know that this is going to be just 0.26 to the power of 4, right? Okay. Now note, for instance, this guy is going to be probability of success 0.26 times 1 minus 0.26, and then we have times 0.26 times 0.26 times 0.26. So we in the end have 0.26 to the power of 4 times 1 minus 0.26. The same thing is going to happen with the third term, that sum, and the last one, right? The last sequence that we have here. So what we have here is 4 times 1 minus 0.26 times 0.26 to the fourth. Okay? Okay. Now, let me here make a, let me make an observation that is going to be important. So let me rewrite, and this is the let me rewrite that probability like this. Okay. This is the same as 0.26 cube times 0.26. Now let's go back to the sequences that we had before. So as we said, the last one has to be a success, okay? Always. So that would be the probability of that last success. Then note something interesting. Ignore for the time being the last trial, the fifth trial. Just pay attention to the first 4, right? So if I wanted you to find me the probability of observing 3 successes in a series of 4 trials, what would be the distribution that you would use? Well, if I wanted you to give me the probability of observing 3 successes in a series of 4 trials, you would go, hey Al, that sounds like a binomial distribution. Is it? They're independent, right? The number of trials is fixed beforehand for each of those outcomes is results in either a success or a failure. So yeah, it satisfies all the conditions for a binomial. So the first part, again, ignore the last trial, could be found like this, right? 4 choose 3, right, times, and then we would have probability of success to the power of 3 times probability of failure to the power of 1. Make sense? Can you see that? Right? Okay. So that 4 that we have here could be re-expressed as a 4 choose 3. We can check. Yeah, that's 4. 4 choose 3, as it should be, right? So let's rewrite that 4 as a 4 choose 3. Now okay, that 1, let's try and rewrite it. Note something interesting here. With this guy, when y was 4, that was the power of 4. When y equals 5, well, it makes sense that, well, we are going to observe at some point, right, 1 failure and then 4 successes. So the sum of these two guys is 5, right? The number of total trials that we needed to find our first 4 successes. But 1, we could rewrite 1 as 5 minus 4, right? Make sense? Okay, let's keep going. Let's try and do one more. Let's try and do 6, and then we're going to generalize for any k that is greater or equal to 4. So let's do 6. Probability that y equals 6. I'm going to write down the first sequence, but then we're going to try and use our observation. Okay? So let me write down the first sequence. In this case, it would be, hey, we needed 6 trials to observe our first 4 successes. Well, that means that perhaps the first 2 were failures, and then we had a sequence of 4 successes. We know that there are different ways for that to happen, but now we're not going to write those sequences explicitly, not for this case, because they would be too many. So let's try and use our observation here, right? So anyway, so if it's going to take us 6 trials to observe our first 4 successes, just like before, the last one must be a success. So that one is fixed. And here, the first 5, the first 5 trials, we are going to have there 2 failures, right? So then we go, oh, or another way of seeing it would be, we have first 5 trials. We want to know what's the probability of seeing 3 successes in 5 trials, right? Again, oh, well, we could use the binomial to find that probability. So in that case, it would be 5 choose 3, right? Probability of observing 3 successes out of 5 trials, right? So 5 choose 3 times probability of success 0.26 cube times probability of failure to the power of 2, right? 1 minus 0.26 square, and those are only the first 5 trials, and then we know that the probability of observing the last one is success, 0.26. So we could rewrite this just like this. So it would be again 4, and 2 would be, guess what, 6 minus 4. Make sense? Okay, so now let's see. When y equals 5, then we have 4, choose 3, right? 1 minus 0.26 to the power of 5 minus 4, 0.26 power of 4. Now that we have 6, it's 5, choose 3. That guy is the same as it was before. Now instead of a 5 like we had before, we have a 6, that 4 again, and that 4 again. So let's try and write the formula for the case when k is any number greater or equal to 4. Here we go. So probability that random variable equals k is going to be, before 6, when we had 6 trials, this was 5, choose 3, then we're going to have, let me write it down like this, k minus 1, choose 3, right, times, let me copy paste this, instead of 6 we are going to have what? We have k. So let's plug in a k, right? And this one remains the same, 0.26 to the 4th power. Makes sense. So we have, when we add these exponents, k, and then we have the same pattern that we had before. So note, another way of writing this down would be k equals 4, 5, ... right? So anyway, see that this is the probability distribution, the list of possible values, okay, along with the probability for each of those possible values. Make sense? So this is the distribution, the probability distribution we were looking for. Oh come on, this is the probability distribution of y, where y represents the number of trials until we observe our first 4 successes. Okay, our first 4 successes. Excellent. Now let me just show you something more from our lecture notes. I think that what I want is here. Yeah. So see slide 120. Well, there we have the definition for a generic negative binomial distribution. Okay, so if a random variable y has a negative binomial distribution, well, then the probability distribution, meaning the formula that gives you the probability of observing a particular value y, is given by y minus 1 choose r minus 1, right? So note that if we go back to what we had here is, oh, in our case r, right, the number of successes that we wanted to observe was 4. So in our case r was 4. So we have y choose y minus 1 choose r minus 1. So that's why we had y minus 1 choose 3, because r was 4 for our example. The probability of success in our example was 0.26. That's the p, right? P represents the probability of success in any given trial. We have the power y minus r. We used k in our example, right? So we have the same, instead of a lowercase y, we have a k, okay? And the possible values, you have to start at r, right? Because if you want to observe your first r successes, well, then you have to try at least r times, okay? One more thing. As you can imagine, right, sometimes we are going to be interested in finding the expected value for a negative binomial distribution, or a random variable with a negative binomial distribution. So we have a formula to quickly find the expected value of a negative binomial distribution. It happens to be r divided by p. Let me make a comment here. It turns out that the geometric distribution is a particular case of a negative binomial distribution. Remember that for that guy, we are interested in the number of trials until we observe our first success. So in that case, r equals 1, and we showed in detail, right, we gave a proof that the expected value in that case for a geometric distribution was 1 over p. And again, so it's a particular case of this expression when r equals 1. So this formula makes sense, right? In the case of a negative binomial, we have r divided by p. And we also have an expression to quickly find the variance of a negative binomial distribution. Okay, well, let's summarize what we did here. Okay, so in this video we introduced a new random variable, the negative binomial. So a random variable is said to have a negative binomial distribution if, you know, you could well, if the probability of observing a particular value y equals this expression. We derived that expression for a particular case, but we realized that, okay, yeah, we could do it like this in a more general way, right? But using the same ideas that we discussed together. And I also presented you these formulas to quickly find both the expected value and the variance of negative binomial distribution. Okay, so that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.